we are once again. It's the physics video lecture. Physics 203, video lecture 28. And I left you last time with the task of proving Snell's law by two methods, and I'm going to go ahead and do that. So what we had was a wave theory, and we ended up relating it to point mechanics, and we finally got down to variational principle and Hamilton-Jacobi theory, and we're going to use that for solving the problem of Snell's law. Okay. And once we do that, we'll recapitulate and continue on. So we have prove Snell's law. And we know from optics, but this is also true in acoustics because we never left mechanics actually. That the law of refraction. So we've got theta 1, theta 2, index of refraction n1 and n2, and Snell's law is that n1 sine of theta 1 is equal to n2 times the sine of theta 2. So that's what we're going to show. And our first method was this, we had this variational principle. It's really Fermat's principle, and that would be n, in our case, n of y, so let's call this x and y. Our index of refraction changes across the x-axis here, so it's only a function of y. In fact, let's even go back to variational principle in the basic form. NdL equals 0. Okay. Good. So with that, we can say, well, we're looking more specifically at n of y, and then our dl is root 1 plus y prime squared dx, fixed boundaries x1 to x2. So there's the variational principle that we're looking at. N of y is a step function. Okay, it's constant on one side, constant on the other with a different value. That'll play a role. Okay, but when we're here, we see that this has the form of f of y and y prime, right? I should state y prime dy dx. F of y and y prime, and not explicitly x, and we remember that we can write df dy prime times y prime minus f is equal to some constant, right? That's our Euler's second form. So let's go ahead and do that. So we will have n of y comes out there, then we'll have 1/2 root 1 plus y prime squared, 2y prime, and then times y prime, we can square the y prime, cancel the 2's, minus n of y root 1 plus y prime squared equals a, and now we just have to simplify this. So we will multiply through by root 1 plus y prime squared. Gives us n of y prime squared minus n of y times 1 plus y prime squared equals a root 1 plus y prime squared. That gets rid of the n of y prime squared, leaving us minus n of y, and we're going to go ahead and square it, equals a squared 1 plus y prime squared. So now we're just going to separate and find this y prime squared. Okay. So we have n squared equals a squared plus a squared y prime squared so what do we get? Y prime squared is equal to n squared over a squared minus 1. Good, so we have plenty of room here. We've got our picture, we have our differential equation, and let's write it this way. dy dx, we'll go ahead and get our plus minus root n squared over a squared minus 1. Now, n squared is a function of y, it's n of y squared. But on the other hand, it's just a constant on one side and on the other. So when we integrate this, it's actually trivial. We're going to get y is equal to, we keep the plus minus, square root of n squared over a squared minus 1 times x. Okay. It's just that this value n, different values depending upon whether y is positive or negative. So I've even thrown away a constant. Okay, so you could say my y of x goes through the origin, just the way I've shown it right here. Okay, good. So let's just go ahead and hold on to this now. With that note, n of y was equal to, n1, y greater than 0, n2, y less than 0. Okay. So we can give subscripts to these different functions below, above and below the x-axis, but even if we write it down as two different functions, which we can, this constant a is the same constant. Okay, that's the important thing. So we would not have different constants, right? We inherited that constant up here. So good, let's go ahead and write that again, a squared. And the rest is just a little bit of geometry. So let's just say, what is n sine theta? N, and then the sine of theta, because the way we're measuring it is always going to be x over root x squared plus y squared, right? It's x over the hypotenuse. Okay, it's the sine of theta, make sure you see that. And then we've got the x, and in the denominator we have the x squared from this one here, it's going to be times 1, and then we've got the x squared or the y squared, which is this square root squared times x squared. So I can just say plus n squared over a squared minus 1. Okay. And you can see now x is going to cancel completely. We're going to end up with n over root n squared over a squared. And n's going to cancel. And yes, it's going to cancel. We're going to end up with a. Magnitude of a. That's fine. So this is the proof, because we have n sine theta is equal to a, and I didn't specify which n. So n1 sine theta 1 or n2 sine theta 2, they're both equal to a. I could even write n sub I sine theta sub I, n sub I and those are gone, and it's just equal to a. So that is the proof. Snell's law. Didn't, no steps evaded here. Good, so we've shown Snell's law using the variational principle, And now we're going to show it using the Hamilton-Jacobi equation. In particular, we're going to be able to get to this equation here, and once we get here, we'll declare victory because we see that the next steps give us Snell's law. So, I'll go ahead and leave this picture on the board. And our second form is, we have the Eichenhall equation, and of course it's the Hamilton-Jacobi technique. So what did we have there? We had omega squared equals c squared k squared, and we turned that into a differential equation. So that was k sub x squared plus k sub y squared, that's those two right there, equals omega squared over c squared. And then we had dc dx plus dc dy squared was equal to this omega squared over c squared, which I named n squared of y. Okay, I'm using capital N, I could use lowercase n. That's because omega is considered to be a constant. C was a function of the coordinate, and in our case, the function of the coordinate is the function of the y coordinate, because we're talking about this same problem here. Okay. So that's our equation that we have to solve. Using the Hamilton-Jacobi technique. So good, let's send this up and see if we can pull it off. And just to remind you, put in the box here, we had ds naught dx squared plus ds naught dy squared equals 2m e minus u, and that would have been the one we used for, say, projectile motion, which also took place in the xy plane. And then this here was a function of the coordinates, and of course that was too. So this is actually going to be easier than this one. And then we would have had S, we would have had S equals S naught of X and Y minus E times T. That was our Hamilton-Jacobi technique, just kind of reminding you. Let's sequester that off here. But we're doing the same thing with the Eichenhall equation, and I'm even going to make it look like the way we did when we solved this. So we have this equation, and we're going to let C is equal to Cx x, Cy y minus omega t, just as we had S was, Sx of x, Sy of y minus E times t. And because n squared of y, because x is a cyclic coordinate, where x is cyclic, so we go in with c is equal to alpha x times x plus c sub y of y minus omega t is equal to 0. Okay, good. So this is our ansatz trial solution. We take this into this equation right here, and our next step is then, of course, the derivative here with respect to x is just alpha x, so we have alpha x squared plus dcy dy, the quantity squared. Now I'm going to do something plus a squared minus n squared of y equals a squared. This is just a move. You notice I've added a squared to both sides. I did this just to make it look like the equation we've solved before. So this will make things look more familiar. Also, you'll see we can either keep this arbitrary constant that we introduced, or we can just drop it. Okay, a couple different ways to solve this. But this looks really familiar. This reminds us of our projectile motion problem. And we also then can say this, because that's just the conserved momentum, and this is a constant. We can say this is alpha sub y squared, and then we could even say this side here, right, this is alpha sub x squared, so we can say this is alpha sub x squared plus alpha sub y squared. A couple different ways to do this. As it is, we're just going to focus on this now, because we already have this in our ansatz, so we need c sub y of y, so there's our differential equation for it. So we have dc sub y dy squared plus a squared minus n squared of y is equal to alpha sub y squared. Okay. This part under the bracket equal to alpha sub y squared. And of course the a squared is going to drop out right away, because this is a squared minus a squared, which is alpha sub x squared plus alpha sub y squared. Other way around. This is alpha x squared plus alpha y squared, so alpha x squared plus alpha y squared minus n squared of y, alpha y squared. So you see these are going to drop away, and we end up with c dy squared is equal to n squared of y minus alpha sub x squared. Okay, this was, again, this here minus n squared, alpha sub y squared. Alpha sub y squared is gone. Brought that over to the right side. That means that I'm going to skip a step and explain it. Remember, this, as before, is a step function. So it's one constant or another. This alpha sub x is for the entire problem. So I can actually write that c sub y is equal to plus minus root n, I could write n sub I squared, because it's the one or the other, minus alpha sub x squared times y. Okay, a couple steps there, but I think they're well explained. There's a minus sign. And again, I'm going to go through the origin, otherwise I could have had an arbitrary constant added to this. Anything else? This will work. So I'm going to keep this side of the board. Well, actually, I can send this up here. Okay, we'll keep that picture again. So I've discarded an arbitrary constant, and if I were picky, I could say this is the function c sub y on the ith side, right? One side or the other, but we'll see in a moment, it doesn't matter. It doesn't matter. Okay, so what have we obtained now? We have c alpha x times x, let's write a plus minus here, root n squared minus alpha x squared times y minus omega t. It's also possible to replace this constant omega with a function of alpha x squared, alpha y squared, and some other arbitrary constant. We're not going to do that because we're just looking for the trajectory, the actual path, so to speak. If we wanted time dependence, we would build it in by putting in the appropriate omega. Okay. But if you want to do that, you can do it. But otherwise, this is just like a constant energy problem where we just leave that. And now what do we know from the Hamilton-Jacobi method? We have a, the whole business with the canonical transformation that we never actually have to do again. But we know that we have a constant beta sub x. We have a constant, once more, okay, we have a constant beta sub x equals deep c deep alpha sub x. And if we can invert the thing, then we're done, okay? So what we have to do is take this derivative here. So beta sub x is equal to, and it's just a constant, is equal to alpha sub, that was equal to x, plus minus, and now we take the derivative here, we're going to have 1 over 2 roots n squared minus alpha x squared, and then negative 2 alpha x, that's that derivative, and that's all times y. So again, beta is a constant, and since we're headed through the origin, we're just going to let beta sub x also be equal to 0. These twos cancel. I'll put a little note about that in a moment. So we're going to get is y is equal to plus minus root n squared minus alpha sub x squared times x. And yeah, our note is beta sub x is a constant, right? Equals constant, we know that. So we let beta sub x equals 0. Sure, so those two constants turn into the putting that, putting that trajectory through the origin. Okay, two other constants, those two constants could have put it anywhere, but we're going through the origin. And oh yeah, this is it. This is the same equation we just, right, that's times x. This is the same formula we just had a moment ago for proving Snell's law. So at this point, it's the same geometry, and you're going to get, well, we had a lowercase n, this time we have an uppercase n, okay. So n1 sine theta 1 equals n2 sine theta 2. And just in case you're not clear on that, our n is equal to omega over c, okay? And the smaller speed of sound, because c is a function of y in essence, okay? The smaller speed of sound gives a larger index, just as before, just as in optics, okay? So there you have it. We've shown that the point mechanics formalism that we've been studying all semester allows us to solve problems in wave theory in the short wavelength limit. Okay. Now we have to come back to all of this that we were doing here. Snell's law, Eichenhall equation was the short wavelength limit of a wave equation. So that's what I'm going to come back to next. That big 2-column chart that I had, I'm going to recreate some of it just to remind us of what we've just done. But you guys could have done this. Maybe you already did it, but I just thought I'd do it again. Good. So we'll start off with a fresh board. Okay. So yeah, this originated in a wave equation, and then we did the short wavelength limit, and that's where we got the Eichenhall equation. So I'm going to repeat a bit of that, not the whole thing, as we move on. Let's set this up here. These two calculations were a form of proof of concept, okay? Because what I had done is I had set up that analogy, point mechanics waves, and by proving Snell's law, which is our fundamental optics equation, you could say, in the basic optics, then we've demonstrated what we had to demonstrate. Okay, so I'm going to start one of these charts again. We'll split the board, start one of these tables again. And this side is waves. So I'll remind you where we started. We never left mechanics, right? We got our wave equation from Euler's equation. So we actually never left mechanics, but of course what we just did with Snell's law we're more familiar with in optics, but we never left mechanics, okay? So with waves, we have the following situation. We have a wave equation in 3 dimensions, say. We got a wave equation. We have C is the root of dp d rho at constant entropy, but more to the point is that it's a function of position. Okay. Now when it's not a function of position, then you have your basic plane waves. Okay. But when it's a function of position, you no longer have the plane waves, and that's where we started off, that's where we generated the Eichenhall equation from. So this is our wave theory, and I don't have to reproduce the entire derivation. Let's see what's key here. So then I'll just write here for the short wavelength limit and that was defined in terms of the regions over which C changes appreciably. Okay. So for that short wavelength limit, we do this. We do V equals A, e to the I, k dot r minus omega t turns into a e to the I constant plus gradient c dot r plus deep c dt times t, close this thing right here. And that turns into a e to the I gradient c dot r minus or plus deep c dt times t. So remember, that was an expansion about some arbitrary point in the space. Okay, this was a plane wave that went all through space in one direction. This is an expansion around some point in space. And for this thing we had omega squared over c squared is equal to k squared, right? Omega is equal to c times k. And so over here we had, we'll follow these lines. Over here we had our k is equal to gradient c, or omega is equal to minus deep c dt. And that's how we got the Eichenhall equation. So then deep c dx squared. So this was just the gradient of c squared, okay? This is a vector. Is equal to this omega squared over c squared, which is where we just were. Okay, is equal to omega squared over c squared. And of course this was, okay, it's all blank. This was that function of position, right? Keep the omega constant, c is the function of position. So that's where that came from with the waves. With the wave equation. And then downstream from this, we had that chart. Okay, so you have that table there, everything I did downstream from here, which I won't reproduce right now. So, good, Eichenhall equation. Very good. So here's how I'm going to break this up, like so. Okay. So this we recognized as being the Hamilton-Jacobi equation. So I had the Hamilton-Jacobi equation here, and I had P is equal to gradient S. I had E is equal to minus ds dt, and this thing here was ds dx squared plus ds dy squared. In other words, gradient s squared ds dz squared equals 2m e minus u, right? If you divide these by 2m plus u equals e, that's just the Hamiltonian, okay? So this was our comparison. And just as c was a function of position, of course u is a function of position for our constant e. So this is why we had this perfect analogy. What I did downstream of all of these things, so down in these columns, was here on this column I wrote down all of the canonical equations, Hamiltonian formalism, and said down at the bottom of this column we had the variational principle, right? And so over here I also had a column that I inherited from the Hamiltonian formalism. And at the very bottom, the variational principle there was Fermat's principle. Okay, so these two, I'm tempted to fill that in again, but maybe you guys can do that. If you look back in your notes, downstream from here, Hamiltonian formalism, Maupertuis principle. Okay, down from here was where we translated the Hamiltonian formalism in terms of these. Some interesting results, by the way. Translated them in terms of these, and then where we had Maupertuis principle here, we had Fermat's principle there. Okay, just renaming the letters, and that's what we've done now. What we've done is we proved the optics problems in two ways using the formalisms that we had here in mechanics. Okay, so far that's where we are. Let's see how much time we're running with. Okay. So I'll even put, I'll put down here, on this side we have Hamilton formalism, canonical formalism, we could call it, canonical equations. And then we have variational principle. If you guys want, you could, you could leave room and fill that in. It's really nice to have this charted out. Okay. And over here we have the corresponding things. So we have equations for K and omega, and then we have Fermat's principle. We ended up with, okay, I'll just write Fermat, etc. Okay, so where are we headed with this? Well, there's a blank up here. This is all point mechanics, classical mechanics. This is the short wavelength limit of a wave theory. Is there a wave theory whose short wavelength limit is classical mechanics? That's the question that arises. That's why I left this here as a blank question mark. Is there a wave theory? Right. Strictly speaking, this is not a wave theory. This was the limit of the short wavelengths took us into geometrical optics or geometrical acoustics. Okay. So is there a wave theory whose short, let's see, better way to write that. Is there a wave theory that gives, this is a better way to put it, that gives us classical mechanics, okay, in a short wavelength or in an appropriate limit? I'll put short wavelength here. Limit. Question mark. Okay. Well, in fact, there is such a theory. And that's what we're going to do next. We're going to just continue these, since we've done all this work here, relating these things, we just have to find the speed of, the speed of sound and the corresponding wave equation. Okay. So that's our task. We want to find the wave equation. Find the wave equation. Okay. There's arrow pointed to the left, right? Okay. So we're looking for a wave equation, which when we take a limit, the same way as we took this one, will deliver the Hamilton-Jacobi equation. Okay. And I should remind us, this, we got Snell's law out of this, geometrical acoustics and geometrical optics as well. But there are many features of waves that we didn't get, interference and diffraction and all those things. Standing waves that we actually talked about. We did cover a bit of the whole wave theory, right? So there's plenty in the wave theory that you don't get. We just got Snell's law, but there's the whole wealth of a wave theory. And over here, there would also be the whole wealth of a wave theory. Okay, I gotta see how I'm gonna set this up now, because I have a number of different paths. Okay, we'll get that later. Good. So here we go. We can even continue our columns for a moment. Okay, yeah, this is fine. So continuing these columns. Okay. Well, I'm going to repeat what I have up here and then start doing the analogous mechanical version. So here we go. We have over here, just repeating what we have, e to the I gradient of c dot r plus deep c dt times t, it's a vector r, phi equals a. Remember, this was a function of the coordinates that changed very slowly. That was a little hand-wavy, but I'm going to assign the rigorous version of this derivation to you guys, which will just be a bunch of algebra, okay? But we'll leave no I undotted by the time we're done with this. Okay, so we have that. Now we can just make our comparison here. Over here on the mechanics side, we have a e to the I, so gradient C corresponds to gradient S, right? Okay, P gradient S. So gradient S dot R, and then deep C dt corresponds to the E, so plus ds dt times t. Okay. That's a gradient. Okay, but there's a problem here, and namely there's a dimensional problem. Okay, this has to be dimensionless, right? Our phase is of course dimensionless, and gradient is 1 over r times r. So the argument of the exponential has to be dimensionless. That means that this object has to be proportional. Well, we'll write it this way: equals a e to the I c, which is where that expansion came from. Over here, we have to have a e to the I s. We need a universal constant that'll make this dimensionless, and that constant just happens to be h bar. Okay. So what you have out of this, by the way, is C equals S over H bar, right? or S is h bar times c. Because remember, these are formally equivalent mathematically, but we have a dimensional question right here. So that takes care of the dimensional problem. And now we have a dimensionless face, okay. So there's the first result. Now again, a couple ways to go here. And in fact, I'll use this. So now we have S equals h bar c. So gradient S is equal to h bar gradient c, which is to say we get P is equal to h bar k. So you recognize that as one of the de Broglie relations, okay? P is equal to h bar k. And what else do we have here? And ds dt is equal to h bar deep c dt. Okay, so I'm just going off of that identity there. And what does that give us? That gives us minus E is equal to h bar times deep C dt was minus omega. So the other de Broglie relation we get is E equals h bar omega. I'll put that right up here. You guys can make it nicer in your notes, but we have E equals h bar omega. So those are the two de Broglie relations. I'll go ahead and put them in the box. Maybe we'll showcase them again. And of course, you know these also as well, you've seen this before where P is replaced by MV, okay, and then K 2 pi over lambda, and H bar H over 2 pi. Okay. So those are the de Broglie relations. Okay. I think it's lowercase d. You guys look it up. De Broglie relations. So far so good. Okay. And these are the considerations that actually led to these discoveries back in the early 20th century, just not as systematically laid out. So you'll find this stuff all over the place in a sense, but you're probably not going to find it in this form, you know, this table here where it's just taken step by step. But yeah, this is where the de Broglie relations fit in. If we're finding this wave equation, and what we did was, you know, take this here seriously, right here, and make the comparison. Okay. So this was required to be true on dimensional grounds if we're going to use the wave ansatz, and that's what we get. Okay, so that's nice. Broglie relations. Okay. Okay, so I'm at the point where I can't keep it all on the board at the same time. I'll have to erase some of this. But we have, yeah, I'll just start this over. Good, we have that. So we're about to come back to the wave equation, but I'm going to erase this so we have some space. Okay, good. I'm gonna repeat the two equations, the Eichenhall equation and the Jacobi equation. So on one side we have c dx squared c dy squared plus omega squared over c squared, right? And on over here we have ds dx ds dy 2m e minus u. That's the Jacobi equation. So we're going to have, by multiplying the whole thing by h bar squared, that's how we're going to identify the left side and the right side. Multiply the left side by h bar squared, the right side by h bar squared. So that gives us h bar squared omega squared over c squared, but h bar omega is equal to e, so that equals e squared over c squared is equal to the right side here, 2m e minus u. And that will give us, for c squared, it's going to be e squared 2m, e minus u. So that's going to be the wave speed associated with our wave theory. By the way, there's another way to get this wave speed, and it's worth doing. So yeah, what I did here, S is just h bar c, right? That's our identification. So I've multiplied both sides because it's squared here, both sides h bar. And then h bar squared omega squared is e, right? Over there, h bar is e squared over c squared. And that's the right side of this equation. Okay, so we have that. So that's the wave speed associated with this. There's a second way to get that wave speed, really just as important. So I'm going to write, note that, suppose we have S is equal to S naught of R minus E times T, okay? And that was in our phase, divided by H bar, that's in our phase. Then ds, so for constant phase, and we're looking for this, the speed of the planes of constant phase, then ds is equal to gradient S naught dotted into dr minus dE dt minus E dt. dt, because E is constant, right? Constant energy. So if this equals 0, what do we get? We get, and let's go ahead and just make the nomenclature like this. In fact, let's do this. Magnitude dl. That means the dr was in the direction of propagation. Okay, so that scalar product turns into the magnitude times the length dl minus E dt. And here's what I wanted to just put a nomenclature dl like that. So if that equals 0, then dl dt is equal to E over gradient S naught. Okay, so that's for the propagation of surfaces of constant phase. Let's put that in words so that everything's complete here. So propagation of surfaces of constant phase. Okay. E over gradient S naught, magnitude. Well, that's E over P, magnitude, and that's E over 2m E minus U square root, and that's dl dt, speed of the propagation speed of surfaces of constant phase, and that is c. So yeah, you see this is consistent. This is going to be the wave speed of our wave theory. Both ways, okay? Yeah, these are good to do this in both ways here. Everything's a consistency check. So both of these gave us the same wave speed. Okay, finally, we're going to get the wave equation. I think that's what we'll end with today because we already got a few minutes going. Yeah, perfect. So the last step we'll do is get these wave equations that we're looking for. The wave equation. We're looking for this. D squared phi dt squared equals c squared del squared phi. C squared is what we just wrote down. 2m E minus U, but now we're making our wave ansatz. And for constant E, we're going to let phi equal, let's see what letter I'm using here. Yeah. Phi naught x, y, z. This is just the way we did x, okay, phi naught x, y, e to the I, but what are we going to have up here now? Okay. We're going to have e over h bar, so e over h bar t, because this is just the ansatz that we would do with the wave equation. And E over H bar would have been our omega, so it would have been our E to the I omega t. Now it's E over H bar. And now we have d squared phi dt squared. So for the left side here, we have I, E, in fact, we're doing a minus I, I'm pretty sure here. Yeah, because when you factor off, yeah. When you factor off kx minus omega t, right? I omega t. So time derivatives minus I e over h bar squared for the two time derivatives, phi naught of x, y, and z, is going to equal c squared del squared phi. So our c squared is going to be right here. It's going to be e squared over 2m e minus u. And then it'll be del squared phi naught of x, y, and z. And yeah, both sides would be multiplied, of course, with the exponential, and would be canceled on both sides. Good, so now it just remains for us to multiply this out. We have e squared minus I, so we have minus e squared over h bar squared phi naught is equal to E squared 2m E minus U del squared phi naught. E squareds are going to cancel, and we'll just simplify this. And we'll get h bar squared over 2m. So cross multiplying h bar squared over 2m del squared phi naught is equal to E minus U phi naught. That's just cross multiplying. Okay, but we have some room right here on the board. So what do we recognize now? We have h bar squared over 2m del squared phi naught plus U phi naught is equal to E phi naught. And that is the time independent Schrodinger's equation. Okay. Right here. So that's where that thing comes from. Of course, we're not done with it yet. But let's get the time-dependent one, and then we'll call it a day. Okay, so we can erase this. Now, to get the time-dependent equation, we'll make sort of a guess, but a consistent one, and then the full consistency check will come later. So for the time-dependent equation, what we do is we look at the ansatz here. Consider, I'll just rewrite it, our phi naught of x, y, z, e to the minus I, e over h bar t. So what we can do here is note that d phi dt is equal to minus I, e over h bar times phi. Okay. Minus I e over h bar is differentiated with respect to time times phi. So there we can say that I h bar d phi dt just by cross multiplying, right? H bar and then I times minus I is 1 is equal to E times phi. Now that's true for this particular ansatz, but if we generalize that, then we can take our E times phi on the right side, and we replace phi naught with phi, of course, take E times phi on the right side and replace it with I h bar d phi dt. So we end up with this I h bar d phi dt is equal to what we had before, h bar squared over 2m del squared phi plus u times phi. Okay. These two equations, you could stack them now as the time dependent and the time independent. I can write h bar squared over 2m del squared phi. Well, in fact, we can ditch the subscript there. Plus u phi is equal to e times phi. And that's where I'm going to leave it for today. Okay. If you leave enough space in your notes, I don't think I've left anything out on how we get, these are, of course, recognizably the equations of quantum mechanics, at least for a point particle in a potential. Okay. So these would be the equations that are used to solve some basic problems. Harmonic oscillator, particle in a box, of course. And if you transform to spherical polar coordinates, then you solve the hydrogen atom. Okay, so of course very important. And the relationship to classical mechanics is exactly as we showed in all of these steps. There's going to be a fair amount left to do now that we have these. We'll save that for next time. Good, see you then.